Hello, welcome to the third video of chapter 2. So in the previous videos, we defined the conditional probability and we learned how to calculate that. And also we learned the general multiplication rule, which is based on the definition, and this is the multiplication rule. Today, we are going to learn a special multiplication rule. So the special multiplication rule is actually you can expect that it says that the probability of the intersection will become simple multiplication between probability of A and B, right? So the result is simple, but it requires a little more study, and it is a very interesting example. So the main topic today is the special multiplication rule and when that what condition is required to have the special multiplication rule here. So let me think about another example. We are going to think of the relationship between tuition and salary. So our question is, does high tuition school pay off? Like say T stands for high tuition. So if T happens, that means a randomly chosen student graduated from a high tuition school. And S stands for high salary, if a randomly chosen person is earning a high salary. So tuition and salary. So we, as I said, we are going to compare the relationship between tuition and salary, whether high tuition implies high salary. What kind of probabilities do you need to calculate? Yeah, think it more carefully. Again, just in case if you don't remember what this means. So probability of S given T means it's the probability of earning high salary given that you have graduated from a high tuition school, right? So the first one is the main event of interest, and second one is the conditioning event. So then in this example, we will compare between those who graduate from high tuition schools versus those who graduated from low tuition schools, right? So the conditions should be different, T and T complement. But what we compare is the probability of earning high salary. So if you graduate from high tuition school, then what is the probability of earning a high salary? Versus if you graduate from a low tuition school, then what is that? Then what is the probability of earning a high salary? So still the main event is the same. So we are interested in the probability of high salary depending on the condition. When the condition changes, whether the probability changes or not. So the answer is B, right? B here is the answer. And then suppose that this is, of course, fake data. Suppose that you observe from the data that 11.25% of people graduated from high tuition school and earning high salary, but 33.75% graduated from high tuition but low salary, like that. There are 4 types of people with this probability distribution. Okay, you get it? So then now I'm not going to ask you how to calculate each of the conditional probabilities. You do that. So calculate those conditional probabilities and determine what is the inequality between them. How do you compare those two conditional probabilities? You need algebra. So pause the video here and try to calculate this. Okay, so if you have not finished your algebra, pause again. The answer is B, right? So we learned how to calculate the conditional probabilities based on 2 by 2 joint probability distribution table. It works this way. So when you calculate conditional probability of high salary given high tuition, you are going to erase the second row. Just use the first row, those who are graduated from high tuition school. So the first row, out of the first row, you are interested in high salary, 11.25. So this is the ratio, which is 25. Similarly, if you change the condition, you are going to delete the first row and use only the second row. And then that's the denominator. And among them, you are interested only in 13.75. That's salary. I mean, high salary, right? So if you calculate the ratio, that is also 25. So what it means is that based on this data, of course, the data is made up. It's not real data. In this example data, it shows that tuition does not affect the probability of earning a high salary, right? So, like either way, no matter which school you graduate from, the probability is always 25, right? This is a special and interesting example, right? So, another thing we are going to compare is this one. Unconditional probability is also 25%, right? So, what is the probability of earning a high salary? That is just these two types. So, you are going to calculate unconditional probability just by adding up these two. The denominator is the whole set. So, that is a denominator is, of course, 100%. So, you don't need to calculate the denominator here. So, what you can see here is it's intuitive result. It doesn't matter whether you graduated from a high tuition school or low tuition school. Still, you are going to earn a high salary with 25%. That means without knowing any condition, you are going to earn high salary with 25%. So, depending on these three conditions, the probability of high salary is always 25. So, condition high tuition, conditioning on non-high tuition, and without any condition. So unconditionally, the probability will be the same. So this is a special case. So we say that those two events are statistically independent if one does not affect the chance of the other, right? So mathematically, you can think this way. Probability of A, probability that an event A happens is the same if B happened or B did not happen, or even if you don't know. Even if you don't observe B, still the probability is the same. And this means this first formula for first equation means that B happening does not affect probability of A, right? So B does not affect A. And mathematically, that is equivalent to the other way, the opposite way. Like B, the probability of B does not change when A happened or A does not happen, right? So, like, they are equivalent. If A does not affect B, then vice versa. B does not affect A. And in this case, we say these two events are independent, statistically independent. So this is super important assumption in statistics, independence, right? Like, because let me interpret the meaning of this definition like this. So you may put different words like that. B is not effective to change A. It does not change A. Or information about B does not help predict the chance of A, right? And between different groups, the outcome of A is the same. So if you compare two conditions, still the outcome look the same, right? So in any ways, they are very useful. and many of our questions are represented in these kind of forms, right? And more concrete examples, like, for example, today's stock returns independent of tomorrow's or not. If they are independent, if today's stock returns is independent of tomorrow's, that means the past information does not help predict tomorrow's. Okay? Or like whether the Chinese GDP growth rate independent of the United States GDP growth rate. It's an interesting question. If they are independent, and then like, you cannot predict what is going on. The global economy is actually nothing. It's just independent. Countries are independent with each other. Then there is no kind of whole global economy, or you don't need to worry about other countries' news. So there are a lot of examples where independence is important as a question, and also statistically, if everything is not independent, that means to predict one thing, you need all the information. So by assuming independence, you can say that I don't need that information to predict something. So it is impossible to put all the data into computer and run something. So you have to assume that this is all we need. And I set a model only based on this information because everything else is independent. Something like that. So independence is a very important concept in statistics. So then, based on the independence, we have the special multiplication rule. So remember, this was the general multiplication rule. So the probability that A and B happen together equals the probability that B happens times the probability that A happens when B already happened. Right? This is the multiplication rule, general multiplication rule. But you may replace this conditional probability to a simple unconditional probability when A and B are independent. A and B are independent, like, remember, when A and B are independent, the probability of A when B happened does not matter, equals to the unconditional probability. So whether B happened or not, the probability of A is the same. So you can replace the conditional probability with unconditional probability. Again, when this is true, only when A and B are independent. If you know that A and B are independent, you can simplify the formula, right? And this rule is also very important. So later, we are going to use this rule again, but it's intuitive. If they are independent, you don't need to think about their interaction. Just multiply probabilities to calculate the probability of happening them at the same time. By the way, one typical confusion is, so I said there are general addition rule, special addition rule, and general multiplication rule, and general special special multiplication rule. So general, special, addition, multiplication. So when we learned the special addition rule, the required assumption was mutual exclusiveness. If A and B are mutually exclusive, the probability of union of A and B, A cut B, equals probability of A plus probability of B. So mutual exclusiveness was the condition, and now we require independence. But mutual exclusiveness and statistical independence have nothing to do with each other, right? So they are totally different things. So even if A and B are independent, they may not be mutually exclusive, and vice versa. So don't be confused. So these assumptions are just to make the rule more simple, and so especially the independent, by the way, mutual exclusiveness is not actually not that important in later chapters, but statistical independence is much more important in the upcoming chapters. So remember that they are different, and also if you if you cannot memorize both of them, statistical independence is much more important. So spend more time on understanding this. So then, now what I'm going to do is I'm going to show you how to test statistical independence. So there are two methods to test statistical independence. So as I said, independence has a lot of practical interpretations and theoretical importance. So we need to learn that. We need to check if two events are independent or not. So I'm going to explain how to do that. And there are two different methods that I'm going to explain in the following video. And thank you for watching, and I will continue in the following video. See you later.